So to continue with this discussion of section 2.2, let's talk about the different types of symmetry and what they would look like in a graph. In the first graph, it says complete each graph so it has the symmetry indicated. So an x-axis symmetry would be anything that's above the x-axis will be a direct image of something below it. I will flip it from one side to the other. So this part of the graph will be flipped over the x-axis. A y-axis symmetry says anything on this side of the graph will be flipped directly over the y-axis. So this part of the graph will move up here. Origin symmetry will do both. Not only will it flip over the y-axis, so this part would then come up here, but then once it flips over the y-axis, then this part has to flip over the x-axis. So ultimately, it's going to move down here. Or you could look at it as a rotation. Anything in the second quadrant would rotate all the way around the origin. And it would end up down here in the fourth quadrant. Let's try another one. X-axis symmetry means this part of the graph is going to flip over the x-axis. Y-axis symmetry says anything on the right will flip over the y-axis. Origin symmetry says anything on the right will flip over the y-axis. Then it will flip over the x-axis. Or you could look at anything in the first quadrant will be spun around the origin and end up down here in the third quadrant. So how do we take an equation and find out what type of symmetry it has? Well, we have to test each symmetry independently. So to test each symmetry independently, we have to test each of them by themselves. So to test for x-axis symmetry, the first thing we're going to do is we'll replace y with negative y and simplify. So let's start with that. If we take this equation and we substitute this y and we put negative y in its spot, if we get the original equation back, then the graph is symmetric to the x-axis. So is this the same as what we started with? Well, you can see that this negative y squared actually becomes a positive. So it becomes y squared minus x minus 4. And yes, it is the same as what we started with, since the negative y squared actually goes back to its original y squared form. Since they are the same, that means that this does have x-axis symmetry. So now we're going to test for the other two types. Now we're going to test for y-axis symmetry. Y-axis symmetry says replace the x, so the opposite letter, with its negative version. So we're going to take x and we'll plug it into the x up here. So it becomes y squared minus negative x minus 4 equals 0. And ask yourself, is this the same as what we started with? Well, let's get rid of the parentheses. Y squared plus x minus 4 is 0. Is that the same as what I started with up here? And the answer is no. Since those are not the same as the original, then that means I do not have y-axis symmetry. The last type is origin symmetry. So to find out if it has origin symmetry, we plug both x in for negative x and y in for negative y. So we plug both negative y in for y, and we plug in negative x. Now if this ends up being the same as what we started with, then it has origin symmetry. So let's get rid of the parentheses. Negative y squared becomes y squared. This becomes plus x minus 4 is 0. So is this equal to what I started with? And the answer is no. They are not the same. Therefore, we do not have origin symmetry. So the only type of symmetry we will have is x-axis symmetry. Let's try another one. So first we test, it doesn't really matter which one you start with, but I'll start with x-axis symmetry. Now let's recall, to test for x-axis symmetry, we take the opposite letter. So we substitute negative y in for y. So up here in the original, we're going to put in a negative y in for y. So that gives me negative y equals x over x squared minus 4, and ask, is that the same as what I started with? Well, clearly not. The left side is now negative. It's not like the negative disappeared. Since they are not the same, that means I do not have any x-axis symmetry. To test for y-axis symmetry, you take the opposite letter, in this case x, and you plug in a negative x for it. So we go back up to the original, and wherever you see an x, we'll put negative x in its place. And we ask, is this the same? Well, let's get rid of parentheses. So this becomes y equals negative x over x squared minus 4. Well, it looks like the denominator and the left side are the same, but the numerator is now negative. So I would say, no, this is not the same, so we do not have y-axis symmetry. The last type is origin. So this is where we plug a negative x in for x, but also a negative y. So you do both. So we plug the negative y into the left side, the negative x in for the x on the right side, and we ask, is this the same as what I started with? So we've got some simplifications to do. Let's get rid of the parentheses. So it gives me negative y equals negative x over x squared minus 4. So the denominator is the same, but the left side and the numerator are wrong. However, there is a trick I can do to both sides of this equation to get rid of that negative. If I multiply both sides of this equation by negative 1 times the left side is going to give me positive y. Negative 1 times the right side is going to give me positive x. And that is indeed the same as what we started with up at the beginning. So yes, this does actually have origin symmetry. Notice that that negative 1 trick was not going to work in either of these. If I multiplied the left side by negative 1 back here, it's going to screw up the right-hand side. If I multiplied the right-hand side by negative 1, it's going to screw up the left-hand side. But it did work for this last one. By multiplying both sides by negative 1, it corrected both sides, therefore leaving me with the same answer that I began with. So in fact, this does have origin symmetry. All right, so let's try to put it all together now. So I've got an equation at the very top, and it's asking me to find the intercepts and then also test the following equation for symmetry. So I'm going to do both parts to be able to graph it. So the first thing I'm going to do is first find the intercepts. So let's find the x-intercept. Remember how we find the x-intercept? We set the opposite letter equal to 0. So that means x squared minus 0 minus 4 is 0. X squared minus 4 is 0. X squared equals 4. And when I take the square root of both sides, I get x is either plus or negative 2. So my x-intercepts are going to be located at 2, 0, also at negative 2, 0. So I'm going to go ahead and plot that. 2, 0 and negative 2, 0 will be on my graph. Then I'm going to go and I'm going to find the y-intercepts. To find the y-intercept, we set the opposite letter equal to 0. So we're going to set x equal to 0. So if I add y to the other side, I get y is negative 4. So my y-intercept is going to be located at x is 0, y is negative 4. So in my graph, 0, negative 4, my y-intercept will be right there. The last thing I'm going to do is I'm going to test now for symmetry. So let's test for x-axis symmetry first. Remember, to test for x-axis symmetry, we test the opposite letter, and is it equal to its opposite sign. So in the original, if I plug in x squared minus, instead of y, I'm going to put in negative y, and I say, is that the same as what we started with? Well, let's get rid of parentheses. And that is not the same that we started with, because the original one had a negative y in the middle position. So no, I do not have x-axis symmetry. And it's obvious here because this point, if it had x-axis symmetry, would have another point up here as another y-intercept up here at 4, but I didn't solve for that point. So I think that was pretty obvious that there was not going to be x-axis symmetry because these points don't have a symmetry point on the other side of the x-axis. So let's now try y-axis symmetry. To find y-axis symmetry, we take the opposite letter and set it equal to its negative version. So when we plug that in, we find negative x squared minus y minus 4 is 0. And we plug that in and we drop the parentheses, negative x squared actually becomes positive. And when that negative actually vanishes, you'll see that this is actually equal to what we started with in the beginning. So yes, we will have x-axis symmetry, which seems likely since this point and this point are both symmetric over the y-axis. So the last type of symmetry is origin symmetry. So let's test for origin symmetry last. So if I test for origin symmetry, don't forget we have to test not only whether x is equal to negative x, but also y. So when we plug both x negative and y negative into the original, we get negative x squared minus negative y minus 4 is 0. And when we drop those parentheses, this is not equal to the original since the middle term was negative in the original equation. So no, we do not have origin symmetry. So looking at your graph and knowing everything that we know to this point, the only type of symmetry we'll have is y-axis symmetry. So every point on this side will also be over here. I think it's fairly clear that this is going to be a parabola, but to be sure, I want to find maybe one or two other points. So if I plug in 1, let's find one other point. So I'm just going to make a tiny little table over here, and I'm going to plug in 1 for x. When I plug in 1 for x in the original, that gives me 1 squared minus y minus 4 is 0. And when I solve for y, that gives me negative 3 equals y. So I'm going to have a point at 1, negative 3. Now, since I've already proved that it has y-axis symmetry, I don't have to really find negative 1 because I know this will have y-axis symmetry, so I know without a doubt that will also be a point on the other side. Same thing over here. Let's say I plug in -3 and I find another point. If I plug in -3 in for x, I get -3 squared minus y minus 4 is 0. So that's 9 minus 4, which is 5, equals y. So I'll have a point at -3, 5 on my graph. And I don't have to find another point because I know it's symmetric to the y-axis. So that means this point will also be on my graph. So for every point you find, you automatically know a second point on the graph. At this point, I think it's clear that this graph will be a parabola. So the symmetry is really nice because you only have to find technically half the amount of points because you know where the other half are going to lie on the other side of the symmetry line. So let's try one more. This time we have this graph. So the first thing we're going to do is we're going to find the intercepts. So let's try to remember how to do that. The X-intercepts. We substitute the opposite letter. We put 0 in its place. So up here, we're going to put 0 in for y. So it becomes 4x squared plus 0 is 4. I'm going to divide out the coefficient. So I'm going to divide both sides by 4. So I have x squared equals 1. So that gives me x is plus or -1. So I'm going to have a y-intercept at +1, 0, and at -1, 0. So I've got 1, 0, and -1, 0 all on my graph. So now we're going to look for the y-intercepts. To find the y-intercept, we substitute x is 0. When we plug x is 0 into the original, we have 4 times 0 squared plus y squared is 4. That's 0. So I have y squared equals 4. So I square root both sides, and I have y equals plus or minus 2. So I actually have 2 y-intercepts. One at 0, 2, and the other at 0, -2. So it's 0, 2, and 0, -2. So this is interesting. It looks like we're going to have maybe multiple types of symmetry because both points are going to have y-axis symmetry and x-axis symmetry. So let's see if that actually shakes out. So now testing for symmetry. X-axis symmetry. Let's recall how we find x-axis symmetry. We take the opposite letter and we plug in its negative version. So we'll plug in y is -y into the original equation and see if that indeed is true. When we plug all of that in, you can see that these parentheses are actually going to drop and this actually becomes positive. So 4x squared plus y squared equals 4 is the original, so that means this does, yes, this does have x-axis symmetry. Let's try y-axis symmetry. To find y-axis symmetry, we take the opposite letter and plug in its negative version. So 4 times -x squared plus y squared equals 4. -x squared is x squared. So you'll see we end up with the original that we started with. So yes, just as we suspected, this also has y-axis symmetry. The last type of symmetry is origin that we will be checking for. To check for origin symmetry, not only do we put in -x, but we also put in -y. So we'll substitute both of those values in. So into the original, we'll put -x and we'll put -y. Negative x squared is positive x squared. Negative y squared is the same as y squared. So that is the same as we started with. So this actually has all three types of symmetry. It has x-axis symmetry, y-axis symmetry, and also origin symmetry. We guessed at the beginning that it was going to have x-axis symmetry because you could see 0, 2 and 0, negative 2 are both symmetric over the x-axis. You also thought it probably had y-axis symmetry because 1, 0 and negative 1, 0 are symmetric over the y-axis. But this indeed also has origin symmetry. Any point on the right-hand side is going to be a 180-degree origin symmetric to any point that's down here in the third quadrant. Because this graph is actually going to be what we call an ellipse. So when I connect these all together, a fancy word for oval is an ellipse. And so you can see that this does have that symmetry. If I didn't know for sure that that's the graph it was going to be, of course I would test another point. I would have to find a point like right in here. Like if I tested like 1/2, so let me try 0.5. This would be really easy to do like in my calculator, since a lot of times we're a little afraid of fractions and decimals. So in my calculator, I would put 4 times 0.5 squared, and that's 1. So I have 4 times 0.5 squared plus y squared equals 4. All of this is 1. So y squared equals 3. Sorry, you can't see that. Sorry about that. So if I take the square root of both sides, I get y is square root of 3. And square root of 3 is approximately 1.7. So I'm going to have a point at 0.5, 1.7. So on the graph, 0.5, 1.7 is right there. And since we know it has all types of symmetry, it's going to have y-axis symmetry, it's going to have x-axis symmetry, and it also will have origin symmetry. So I can find the other 3 points based on that one point.